expression that we found for the electric potential due to a disk of charge to find the expression for the electric field of a disk of charge. So we found that the expression for the potential was 2kq over r squared times the square root of r squared plus z squared, take away z. There's our potential. We want to find the field. So the electric field equals, we have to remember that the electric field is a vector. When we find our answer, it is going to be an answer given in unit vector notation. The direction will have to be given. Let's remember what potential is. It's the gradient. Let's remember what electric field is. It's the gradient of electric potential. It tells us about the change in potential. What that means is that the x component is the derivative with respect to x. The y component is the derivative with respect to y. And the z component is the derivative with respect to z. So let's do each of our derivatives, then we'll write our answer as a vector. Let's do our derivative with respect to x first. So ex is minus di by di x of 2kq over r squared times the square root of r squared plus z squared minus z. We see that we have no x dependence here at all, so there's no variability with respect to x. So the derivative with respect to x, the change with respect to x, is 0. Our derivative with respect to y, similarly, is also 0. So then the last part we have to find is what is the derivative of this function with respect to z. So let's take our constants out front. We have minus 2 times k times q over r squared times the derivative with respect to z of the square root of r squared plus z squared minus z. So for our derivative here, we can do it in two parts if we wish. So the derivative of the square root of r squared plus z squared is the derivative of r squared plus z squared to the 1/2. So we'll get 1/2 times r squared plus z squared. When we do our derivative, we have to subtract 1 from our exponent, so this will be 1/2, subtract 1/2. Then we do our chain rule, we find the derivative of what's inside, that's 2 times z. Then we can write this a little bit more neatly. We get z over the square root of r squared plus z squared. Okay, so there's the first part. We'll also need the derivative of minus z. That one's really easy, that's just minus 1. So now we can fill in these parts right here. So there's our x component of electric field. We could leave it like this, but I think I'm going to multiply that negative sign in through. So there's our expression for the electric field. If you wish, you can take this one step further, and this would just be to compare to the result for the electric field as given in the textbook. So you may, if you wish, use that k is 1 over 4 pi epsilon naught. And then from our charge density expression, the density is q over pi r squared. Means that q would be the density times pi r squared. So if you wish, you can substitute those guys in. So 2 times 1 over 4 pi epsilon naught times eta times pi r squared divided by r squared, 1 minus z over r squared plus z squared. Okay, simplify this a little bit. Pi's cancel, r squareds cancel, 2 goes into 4, leaving a half. So we've got eta on top over 2 epsilon naught, 1 minus z over square root of r squared plus z squared. You didn't have to do this, but you might recognize that this is the same result as we found before. So when we were working on finding electric fields by integrating over the solid object, this is what we found. We're still not quite finished the problem. This is the z component. We still have to write our electric field as a vector. So the x and y components are 0. We won't write those down. We're left with the z component. So our electric field vector is eta over 2 epsilon naught times 1 minus z over square root of r squared plus z squared times k hat. Okay, so there's our electric field. Again, this process is probably a little easier than integrating the electric field over the disk, because when we find the potential first, we don't have to worry about finding the components.